All right, we should be live. Good evening, ladies and gentlemen, and computer students. You sure? It's
Really hear you.
in the Zoom.
Yeah, sure.
There's someone right back there. Can everyone hear me okay?
Yes.
Okay, I got one yes. So I'm just gonna hope. I think I can hear some degree of microphoning going on. Welcome to the Computer Systems Revision Workshop. This is my second time haphazardly involving myself with this last minute. Shout out while we start here at the start to Aisha Ahmed, who moved to Sydney and maybe New York, I don't know. Did really well in computer systems, wrote a whole bunch of slides for revising, which we have tweaked because the content has shifted a little bit year to year. So hopefully what we've ended up on is something that is relevant and useful. And hopefully I don't get bamboozled by too many slides that I didn't actually get all the way through checking. We can start with an acknowledgement of country of the Wurundjeri people of the Kulin Nation, the people who were here quite a while ago. I put this in as something a little more interesting than just the usual one. Has anyone seen this building? Like, surely you've all seen this building. Has anyone got a tram up Swanson Street to the uni? This building sticks out. It has the call it the pod races on the other side of it. How do I do a new window? There's this guy. His name was William Barak. Yeah. Oh, sure. Oh. Sorry, the people on the screen might be missing it. You can look this up online. This is the way you might know. It has the cool color blobs on it, but it has this white stuff on the other side. And turns out, oh my goodness, how do I, here we go. Cool, we're back. Turns out it's a guy. You can see here on the left that it's a guy. His name was William Barak. He lived through the...
To change your screen sharing if you wanted to show it.
Oh, that's fine. It's all good. He's a guy. He's an Aboriginal guy. He had a lot about Aboriginal rights and stuff like that. And I was reading on the way here. He settled in an Aboriginal farming community near Healesville, which is like 50 kilometers away from here. And Barak and other elders walked from there to Parliament House, Melbourne, to approach parliamentarians directly several times, as well as using newspapers to further their cause. So the more you know. If you've seen this, it's a guy. He was well known, and I encourage you to read a bit more about him if you're interested in Australian history. So yes, disclaimer alert. This is technically not officially endorsed by the uni. We were reached out to from CISSA and MISC to help facilitate this. I've been involved in it before. It was a wonderful surprise to find the diagrams I did on the fly 2 years ago in the end of this workshop. So yeah, I've done it before. So yeah, but it's unofficial to some extent, but hopefully you'll get some use out of it anyway.
Who are you?
Oh yeah, I should give an intro. My name is Stuart Webb. I finished a Master's of Computer Science here in the end of 2023. I got really lucky in Masters. I did exchange and got to go to ETH Zurich in Switzerland, which turns out is a really, really, really good computer science uni. And they do a subject there called Advanced Operating Systems, which is insane. We built an entire operating system all semester. And it was based off a research microkernel they made there called Barrelfish. It's crazy. Barrelfish showed up on the front page of Hacker News today.
Okay.
The more you know, you can go check it out. It's really interesting. Another Aussie guy worked on it, Andrew Bauman. The more you know. Anyway, I did a thesis on operating systems and programming languages. And then I got a job. Now I work at Commonwealth Bank as a systems engineer or a platform engineer now, whatever that means. We do a centralized logging solution for like all of their servers, which is insane. It gets like 40 or 50 terabytes of data through it a day. Corporate scale. It's interesting. So yeah, that's me. I've been tutoring this subject. This is the third time I've done it.
You've been what now?
Sorry?
You've been what now?
Tutoring the subject? What did I say? I don't know. Oh yeah, no, I have been peripherally attached to this subject through student connections for a number of years, due to my interest in operating systems. And yeah, I have run this before to help out with it. And I've got Bryn with me as well, who I can hand over to for a brief intro.
Sure. All right. Hi, guys. I'm Bryn. I've also been peripherally attached to this subject for a couple of years now. I did this subject back in 2023, found it was a bit of fun, and learned quite a bit from it. Alongside that, I'm still in my undergrad, as some of you might know, and currently working as a junior security engineer. Before that, I was a software engineer, and now I'm here making workshops just because. Cool.
Alrighty, and big thanks to CISSA and MISC for organizing this. If you're in CISSA and you don't know MISC, they're the Information Security Club, I think. Hacker people, smart people from my experience, like the more I go through industry, like the cybersecurity people, they're the giga nerds, they know everything. I think I may end up in cybersecurity at the rate things are going, but anyway. And then if you don't know CISSA, CISSA is for computer science students and so on and so forth. Okay.
Can we come up and do a quick plug?
Oh, yeah, sure. What are you plugging for MISC or CISSA?
CISSA.
CISSA. Okay.
Thanks. Sorry, just thought we'd briefly say, if you guys don't know CISSA, pretty cool club. It's sort of a big one for computer science at UDML. If you'd like to find out more, maybe scan the QR code. We have lots of cool events, both social and more practical stuff like this. Thank you.
Thanks. And for MISC, if you guys don't know, it's just on cybersecurity. So if you like making things and if you like breaking things, maybe come along to some of our workshops and learn how to do that. Yeah, that's the sign up code.
Even if you don't get all the way through, you'll probably learn a lot. So that would be my recommendation. Okay, so to start, I hope this isn't too daunting, but I tried to make a dot point like summary of the content in this subject. There's a lot in the subject, but what we want to try and do is like, I think the easiest way to do this is we'll ask the room topic by topic whether it's a topic that you would like to see covered in detail or not, and we will try and gauge things through that. So raise your hand to some degree of percentage to represent how interested you are in us covering the topic.
Just do like high level overview.
Hmm?
Say, all right, I'll add some.
Okay, well, yeah, so there's three. This is the famous, it's the subject with two halves and 2 weeks of cryptography in the middle, but 1 week this year. So there's a side on operating systems. Then there's a week this year on cryptography, which relates between operating systems and networking. That's like interlocked between them. And then for the networking side, it's all about going from physical networking up to like the interface level in programs you write for communicating with the network and trying to explain and understand how all that works, including the internet. So this is a high level overview. All right, let's just go through them quick. General OS overview, OS purpose. Hopefully that's really straightforward. CPU mechanics, so interrupts, syscall, and kernel user mode. Cool. Processes. Threads. The distinction between threads and processes. Synchronization and mutexes, so like mutual exclusion, things like that. Okay, we've got finally some hands. All right. Virtual memory, which includes paging and other things like that. Okay, cool. Got a bit of interest. Scheduling, which kind of covers processes, I think. Okay, cool. I'll head over to Bryn for crypto.
Sweet. All right. Are we all kind of familiar with secure communication? Anyone would like to go through that? Just the fundamentals of crypto. Great. What about thinking about how does confidentiality work? No, excellent. Differences between asymmetric and symmetric encryption and a bit more about how they work. Nope. What about hashing? Okay, sweet. Message authentication codes. Okay, fair enough. What about digital signatures and certificates and that whole public key infrastructure stuff? Cool, good to know.
What were the main ones you wanted that you've got?
Hashing MAC digital signatures and sets.
Okay, last four. Okay, cool.
Go.
Okay, cool. And back to the network side. So at the high level, we have the OSI model / TCP/IP model and all of its layers. Okay, cool. application level program. Actually, yeah, well, all right, fine. I'll do it the subject way. Application layer protocols. So starting at the top. Okay, a lot of interest. Transport layer protocols. That covers TCP, UDP. Okay, a lot of interest. Network layer protocols like Ethernet and MAC addresses. Perhaps the most interest. This is great. TCP sliding window. Okay, every year. TCP congestion control. Again, okay, cool. Networks and subnetting. Okay, cool. So it sounds like basically everyone wants to look at the networking side of things. That's fine. If that's the case, sorry?
Routing.
Oh, well, yeah, and routing between networks. I guess that kind of falls out of subnetting to some degree. We will explain. So if that's the case, let me skip through all of the slides that we put together for our operating system. These slides will be made available to you. And Aisha's idea when she put them together, she said somewhere at the start that they're very text dense to try and just give you a lot of information and help search through. One general thing I always say to people who are studying this subject is that it is dense. And what's difficult about it is that there are so many different concepts involved and they all kind of cross-relate to each other. It's true in the operating system side. It's like, what does the CPU do? What are registers? Well, they're part of the CPU. Okay, so what is virtual memory? Okay, well, that's controlled by the MMU, which is attached to the CPU. And it involves the CPU's access. It's like, it's this big mesh, basically. And so the best advice I can give is to try and like develop your understanding of that mesh. And explain to this person now, so this advice is less pertinent, but don't freak out too much if you don't understand everything on first go, because the more you go through that mesh, the more of an idea you've got of different pieces and the more the links will start to make sense. So yes, there's gonna be a lot of slides to get through. I feel like there's two interesting things I'll quickly touch on. I always give the analogy that the CPU is like an instruction monkey and it has a big like paper list of instructions, which are the next code to run and stuff like that. And in general, all it will do is go next instruction, next instruction, next instruction. But there's like there's three exceptions to that. And they're actually, one of them's not technically here. The first technicality is that programs can have a jump instruction, right? The jump instruction can cause it to go somewhere else. So technically that's not next instruction, it's like a jump or whatever, or a call of a function. But then in addition to that, interrupts and or exceptions, I like to describe it like the monkey gets hit with a hammer and it goes, argh! And so it like knows because it got hit with a hammer, it has to go do something else. In the case of interrupts and exceptions, that's like somewhere specific. And system calls are kind of similar. They're usually implemented by a software interrupt, especially in x86, I think. But that's worth just keeping in mind. It's like the CPU is this like little monkey you have to wrangle. That's what the operating system's job is. It's to control the monkey and make it do the right thing. And ensuring that like its behavior is well understood. You can go read all 5,000 pages or whatever of the Intel x86 manual if you really want to. Like it's quite clearly specified what it does and how it behaves. So you have to use that. An operating system uses that as the basis for building something more useful. System calls, interrupts. This was the thing that we wrote. So when interrupts happen, there's this interrupt vector, which is a special area in memory of addresses of functions, basically. So like inside the kernel, I'm pretty sure, there's a bunch of functions for handling interrupts. And then pointers to those functions get put in one array somewhere, and that's the interrupt service vector or the interrupt vector. And basically, when an interrupt happens, there's usually a number associated with it. And that number is like the cell of that array that it goes into. So when the monkey's, the analogy I give is the monkey's hit with like a particular color hammer, or like it's a hammer that plays a particular note or pitch. And the monkey knows that it's like, oh, I played a C sharp. So that means I go to the C sharp function and handle it from there. And the examples of this, you probably know, mouse interrupt is like, where is the mouse now? It just updated. Keyboard, what key was pressed? And then for disks, when hard drive data happens. An interesting thing that often gets missed in a lot of the coverage of this subject is like timer interrupts. This is something I discovered many years later. They are like one of the core functions of multi-processing operating systems. Because if you think about it, right, if we go back to that list of 3 things, like how can processes switch between other processes other than any of these mechanisms? There is no way to do it, right? So there's something covered in one of the later slides about how it's great. I can see through more of the slides. Yeah, here we go. Implementation. So how do we obtain the illusion of multiple parallel processes on the CPU? And in the history of computers, they started by using a thing called cooperative multitasking, which is where, like, it's similar to the yield mutex, if you remember that. Like, you have to make a yield system call, which is like you telling the operating system, all right, I'm done with the CPU. Someone else can have a go. And the analogy I always give for this is, yeah, it's my turn on the Xbox or whatever. But that doesn't always work if you've grown up with siblings or whatever. This is the analogy I give. It's like, if it's your turn, the other person's not going to give up the controller necessarily, right? So sometimes you need mum to come along and it's like, mum said it's my turn on the Xbox. And in preemptive multitasking, that's the interrupt hammer that makes that work, right? Because that interrupt comes from a timer that goes off, like, say, every 50 milliseconds, right? That's always going off. It always gives control back to the kernel. That's how processors switch between each other all the time on the basis of computer running. So hopefully that makes sense and is a useful explanation. It's like I say, it's just something that was always missing, I thought, in the way stuff was explained in this subject. I filled this in with some details of some of the stuff that happens. When an interrupt occurs, the CPU registers are right in the middle of a program running, right? Like if you've looked at assembly code, it will like load an address from memory into register 3, multiply register 3 and 2. When the interrupt happens, it's literally right in the middle of that. And so all the registers are in some state, and that needs to be saved somewhere before anything else can be done. And that's what happens here, is that it's actually in the interrupt service handler. That's the thing that does it. Like, that's code that actually will save everything into kernel area memory associated with that process or whatever. Then it'll go to the interrupt thing and it's got its registers free to do things with. And then when it's finished, it goes, oh, okay, well, what process are we going back to? Are we going back to the same one or another one? That means invoking the scheduler. And then on the basis of that, you find the right registers and refresh them, like put them back into you get the values, put them back into the registers. And then you call this return instruction that will jump back to user space into the address space of the process that you want to run. And the instruction pointer will be set back to wherever it was when it last left off. And at that point, all the registers are exactly the same state that they were just before it last left. And it's on the next line of code. So it's as if nothing happened. So that's part of what happens with context switching, so to speak. We'll have to skip through all of this. Yet with threads, the general thing is when you have multiple cores, you can't take advantage of the multiple cores within one process, because the process alone is one schedulable entity. It can't be split up to run multiple times, like it'd be multiple processes. So that's why you have threads within a process, because if you've got like a quad-core CPU, you can't make use of the fact that there are 4 CPUs unless you have a thread per CPU in your program to be able to have them get scheduled onto the different cores to run truly concurrently. But there's a trade-off as well, that another important thing about threads is lots of system calls, especially IO system calls, block, right? You would have dealt with this in the project. You know, if you call read or accept, your thread blocks. Nothing else happens until that is handled. So by having multiple threads, you can have different threads block at different times. And then because the threads are all constantly rescheduled, it means that only one part of your program gets held up on the blocking thing and other stuff can still happen. So that's it. What else is here? Just do this.
Wanted to touch on paging a tiny bit, I think.
Oh, yes, paging was the first topic. Okay, cool. Synchronization was the other one. One slide we didn't get around to quite preparing, but that's fine. We'll work through something on that. Virtual memory. How do I start with describing virtual memory? it's really best motivated when there is a picture. I wonder whether how fast could we bring up? We'll see if we can do this later. I think I have a picture or two that kind of helps motivate this, but virtual memory, there's two things to kind of cover here. We go back to here for memory management. In the history of sorts of computers, or a loose progression from basic to more advanced, I always give this analogy. Does anyone here know what a Commodore 64 is? Got one vague hand. It's a really old computer. It's from like the 80s or something like that. To use a Commodore 64, it can only run one program at a time. They come with like a tape drive, and like you put a cassette tape into it, and then you type load program, and you push play on the cassette tape, and it starts playing data, and that starts loading it into memory. And then when it's finished, the program starts running. And you can't switch between programs unless you load an entire new program into memory. So that's how like computers used to be ages ago. And so then multiprocessing kind of came along and was like, well, it would be useful to have multiple programs running on the computer and the ability to switch between them. And memory segmentation was one way that was done. I don't think it's covered that much in this subject, but it's like a primitive way of locking off areas of memory and swapping between them on the basis of swapping between different programs. But virtual memory kind of came along at a certain point to facilitate two things. Like the first thing is these advantages we've listed here. If anyone's done microprocessor development, microprocessors usually don't have an MMU. They run one program that you kind of have to load into it, and there's one memory space. And because of that, like, if you load other code, like all the memory addresses are one space. So like, you can't just have multiple programs running that can all assume the same thing about memory. Like if you need to load a chunk of code in, for example, it needs to be given its own space to run. This is kind of the fundamental problem with trying to run multiple programs at the same time. You don't want them to step on each other's toes when they're making use of memory for storing data all the time. So paging was one way of doing this there's this thing of simplifying addresses for when processors swap in and out. If you just use physical memory for splitting up space for processors, every time you run a new process, it can potentially be in a new different area of memory, and the whole program would have to be relocated or rewritten to be able to make better assumptions about where in memory it's operating for. You can't just say like, oh, read address 207. Like it has to be 207 as an offset of wherever you were loaded into memory. So the advantage of virtual addressing is that because everyone gets their own view of memory in this little virtual bubble, you can just start making reference to fixed addresses and it's fine because they're kind of abstracted away. So that's one of the key reasons why virtual memory exists. Hopefully that helps motivate and explain it a bit more. For the other advantage is paging. So that's where this thing says, if you want to work through more data than can be fit into main memory at once, like you can't keep it all in memory at once. You need to be able to take bits of it out. And that's where paging is really helpful because it's a mechanism that allows doing that because pages can be marked as in or out of memory. And that's where this mechanism comes in of, because the paging system is always invoked or used every single time memory is accessed, that means the page table information is always checked. And as a consequence, it'll check whether it's loaded into memory or not. This is like the present bit or something like that that you may remember from descriptions of virtual memory. So even though not everything may be there at any one point in time, whenever it's used, it is brought back into memory. And that means it's fine, basically. So yeah, for virtual memory to continue more, like I think I'm going to need a diagram and we'll have to come back to that.
There's one of the questions that we'll give out.
Yeah, okay. Because to get into the mechanics of it, like you need to have an MMU, a page table, you need to step through an example of the base address, the page offset, things like that. There is a workshop question on this. Hopefully you've all done it. Doing it like that makes it make sense. It's the same with the TCP stuff. If you do the flow diagram, it makes it make sense. I just noticed there's like 6 questions. Okay, someone else is handling it. Oh no, oh no. Where's the, not sure. Okay, we're back. So, sorry, I said I was going to skip all the OS stuff, and I've talked about a bunch of the OS stuff. This is where we head over to cryptography. Do we want to do cryptography or do we want to do networking?
What would you guys like? Go through cryptography?
Hands for cryptography.
All right.
Hands for networking. Damn, that's like 50-50.
Why don't we just overview cryptography with the slides?
Okay,
It
sure.
shouldn't take too long with it. And
All right, and then, yes,
Can you explain the map bit? I think that was.
for
message authentication code. Yeah. Okay, cool. Absolutely. Bryn can help explain that. And we will take a break after this because I sped through the OS stuff. So,
all right, hello guys. Also, if you have any questions for OS, hopefully there will be time at the end. And if you have any questions throughout for crypto, feel free to raise your hand and we can discuss it. Cool. Okay, so crypto, what are we trying to do? We're trying to form 3 things. When we send a message, we don't want anyone who isn't the receiver to be able to interpret and understand it. We want to be able to have different parties be able to say who they claim to be, right? So obviously we can't say who we actually are. So there's only some degree to how far we can authenticate ourselves. But generally with authentication, the idea is I have something that can properly certify I am who I say I am. And that comes into the verification component too. Lastly, we also want to be able to verify the integrity of the messages that we send. So from a networking standpoint, that's as simple as calculating a sum or value and putting it in the packet to be recalculated on the other side. You may have heard of a checksum, which as part of reliability will be covered later. From a cryptography standpoint, this also includes maybe the idea of a shared secret key, where the sender will calculate a fixed value using the secret key, and then the receiver, using the same secret key, should be able to calculate the same value. This way you can verify integrity, which is that next stuff you guys are a bit nervous about. Cool. So you seem to be already pretty confident with encryption and decryption, but just for thinking about things like the exam, when you're answering cryptography questions, please pay attention to your primitives. So that is this encrypt M key business and decrypt CT and key. So when we're encrypting, we're taking this plain text message and we're converting it using some form of key to a ciphertext, which is just a garbled mess. Then decrypting is essentially reversing that process. Now, cryptography, not a perfect science. You can generate every possible key. The aim is to have algorithms that make it infeasible to do in a reasonable amount of time, usually trying to outlast the lifespan of the message. Any questions so far? No, great, cool. Okay, so symmetric cryptography is essentially we can encrypt and decrypt with the same shared key. This works by breaking up our message into different blocks, each of a fixed length, and encrypting and decrypting them in parallel. That's the gist of it. It's pretty fast compared to your asymmetric cryptography, which we'll get into in a sec. And it's, as a result, it allows us to use it for things like full disk encryption. And maybe if we want a real-time encrypted chat, we might use symmetric cryptography. Cool. All right, so there are 2 modes of symmetric cryptography. We have this idea of electronic codebook. Now, hopefully this at the bottom will be familiar to a few of you who have watched the lectures, the good old Linux penguin. So when we encrypt something through electronic codebook, what happens is we have a tendency where we can preserve patterns in the encrypted message. So as you can see, encrypting the penguin, you can still sort of see the penguin, although it's at a lower fidelity. This is because electronic code book doesn't have any introduced randomness, and so it lacks diffusion. As on the slides, diffusion is quite simply for some part of the data on the input, on the plain text. If I have an algorithm that has high diffusion, that should be able to affect several parts of the data on the output. So 1 bit in the message plain text might be able to affect what the output of several of the bits in the ciphertext look like. The gist of this is for each block, you can encrypt them all in parallel and you can decrypt them all in parallel. They're independent of each other. Cool. So to combat this, the idea that we can still see patterns in the ciphertext after encrypting it, we have cipher block chaining. So now we have this idea of an initialization vector that is sent across with our encrypted message. And what this allows us to do is before we encrypt each block, we can do this thing called XOR with the plain text. Now, quickly, is anyone able to tell me what XOR is? Just yell it out. Exclusive OR, great, what's that?
It's like the logic gate. It's when the two inputs are a bit different than the outputs one. And that's the only.
Yep, great. So exclusive OR is like OR, except when the two outputs are the same. So the two inputs are the same, the output is false. And when the inputs are different, so 1 and 0 or 0 and a 1, then the outputs are 1. You might also be able to think of this as equivalent to being not equals. So if two things are equal, it's false. If they are not equal, then it's true. Easy. XOR is quite fundamental to a lot of cryptography. I won't get into that too much. Just know that it's involved in cipher block chaining. As a result, we can't encrypt in parallel because each block relies on the block before it, with the initial block relying on the initialization vector. However, we can still decrypt in parallel because we have the ciphertext of each block. Now, quick recap, what happens when we send the initialization vector and the message? What happens when the initialization vector is corrupted or missing? How many blocks do we lose? Got 1 vote for 2. Who else agrees with 2? Okay. So we lose the initialization vector when we're decrypting. So we cannot decrypt the initial block, but we should still be able to decrypt the second block after that, I believe. Correct me if I'm wrong.
Again?
So we lose the initialization vector, and we can't decrypt the first block, but we still have the ciphertext to feed into the next block after that.
Yes.
Yeah.
Yeah, and the key is the same at each step.
Yep.
So even though you lose the one block, you don't lose all of them, luckily. Which is
Yeah.
not the same as other ones, I think, because if you were to feed the ciphertext,
I think that works.
actually, yeah, check.
Okay, so because
Sorry, in the encryption state, sorry, this is in the encryption state, you do need to take the output of the block cipher at each step.
Yeah.
So, for encryption, I think the encryption has to be synchronous, right?
Yes.
Like you can't split it up, but the decryption is different.
yes,
So, yeah.
decryption is parallel. You lose the IV, then you can't decrypt the first block, but you still have the
So you can tell the
ciphertext.
rest because, yeah, the reason for that is because you've already got the ciphertext when you do. Yeah,
All right, so after a bit of deliberation, yes, we have we lose the initialization vector, then we only lose the first block because we have the first block of ciphertext for the second and so on and so forth. However, as in one of the tutorial questions that I definitely have not seen, if you lose one of the blocks of ciphertext, then you cannot decrypt that block or the next block after it because it is required for XOR. However, because it's random, this means we no longer get the patterns that we see in our Linux Penguin here. Because the output, if I had 2 blocks that were exactly the same as plain text, they would be encrypted differently as ciphertext, because one would impact the outcome of the other, giving us that high diffusion. Great. All right, so quite simply, we cannot encrypt in parallel for CDC because one block of plain text depends on the ciphertext of the previous one, but ECB, everything is independent. So we get a yes, yes, yes. However, CDC, we can decrypt in parallel because we have all the information we need to decrypt any block we want. And this idea of random read access is if we wanted to decrypt and just like yoink out a piece of data, then we would be able to do that without having to rely on any other thing to read it. Okay.
Yeah, no.
Great. Okay, now moving on to asymmetric cryptography kind of quickly. So before we had one key, now we have two. Each party that wants to communicate has a pair of keys, public and private. The public key is out in the open and anyone can encrypt anything with it. The reason that this works is because the private key is kept secret, hopefully, and is used to decrypt any of the information that is encrypted with the public key corresponding to the private key. As a result of the way that this is generally implemented and the key sizes involved, asymmetric encryption is slower than symmetric encryption for the same message length. As I mentioned before, private key, so it's more secure. You don't have to think about this idea of a key exchange, where with symmetric encryption, you have to think, well, if I'm trying to communicate with Stuart, how are we going to share the key ahead of time securely, such that none of you can see it? Cool. It's also used in digital signatures, which we'll get to as well, where you get this idea of non-repudiation. Great, so this is just an example exchange of a message using only preserving confidentiality. We aren't caring about the other two just yet. I'll leave this for you guys to study in the slides at your own pace. There should also be a question after that we will give you around that, so maybe pay attention to it. Cool. Similarly, here's how we might exchange a shared key. Once again, I recommend you have a look at this in your own time, in the interest of keeping time here. Great, hashing. Okay, so hashing is one of the ways we can both verify integrity and also kind of mitigate this idea that asymmetric encryption is slow. If I want to encrypt the entire Shrek movie, it's going to take a long time, right? It's a big file. However, if I were to hash it, I can get a very fixed length representation of it, a hash digest, and then I can encrypt that, and that can give me a representation of the Shrek movie. Granted, not very useful because we've compressed it, but we would be able to use this as a signature to say, this is the Shrek movie. Great. Okay, so what is a hash? It's something that, yes?
When you said that hash was used as a signature, then it's the top of the digital signature.
Yeah,
I
well,
think, did you mean that
it's used as part of a signature.
when you produce signatures, rather than signing the whole Shrek movie, which will take you a bit of time, if you sign a hash of the Shrek movie, and the other person's got a copy of it, they take an MP5 of it, then they can check that, and that's a lot faster. And it'd be crazy, well, in theory, crazy hard for someone to have flipped the bits in a way that it's not the Shrek movie or whatever.
Yep, so
Yeah, so I think in PDFs, often signatures on PDFs are the hash of the content rather than the PDF, because PDFs can get really big, right? Yeah, there's, I think I can show about that.
the crux of the idea is we're using a hash to first make the file smaller while still keeping a unique representation of it. So generally speaking, a good hash function is going to be one way. So if I only have the hash of something, I should not be able to reverse it. That is what makes it different from decrypting. So if you're ever storing passwords as part of an authentication implementation, please do not store encrypted passwords. They are reversible. Hashes, a good hash should not be reversible. On top of that, it should be collision resistant. So I should not be able to find two values that are different as plain text that equate to the same hash for a hash function. So I put MD5 up as an example that is not a good example of collision resistant anymore. And here's a GitHub that demonstrates this quite well.
Can I quickly go as well?
Okay, sure.
Sorry, this is relevant, I swear. So this is going here. How do I get back to this one? Yeah, okay.
Yeah,
And we have to, how do we, oh my God.
Would you like to take the mic?
Shadherd.io. So this came out, it's according to what I'm reading, in 2017. Some researcher nerds worked out how to break SHA-1. And this actually talks through it quite interesting. There's a whole research paper on it if you're interested. But it uses PDFs of these as the example, like signatures are produced of the hash. And they found a way to inject junk into a PDF alongside genuine changes to the PDF such that you could still get the same hash. So say you got an official document from someone and it's signed as a verification of authenticity. And I'm trying to think of like something that would be worth impersonating.
Stat deck.
Yeah, stat deck. I am going to destroy your house and beat up your car or whatever. That would be unexpected, right? And if you saw the signature, you're like, oh, damn, they really mean it. They signed it. So the ability to change it and keep the signature by fiddling with that content, but fiddling with it in a way that the hash is the same, that's the collision problem. So you can look more into this if you're interested, but this is a quite practical example of hash collisioning going wrong, or an attack on it, so to speak. Oh, there we go. Trick someone into creating a high valid signature for a high rent contract by having them sign a low rent contract or whatever. So yes, we need to resume and we need to slideshow.
Yep. All right, cool. So takeaway here, hash is meant to be one way and you're not able to find two inputs that lead to the same output. And inputs that are very similar, as with high and high with two eyes, should lead to wildly different output, which was the case for MD5 for a lot of inputs. Any questions? No? Great. What's happening now? Okay, Max. So now we think about integrity a bit more. And this is probably what you're all here for crypto. So Max are there to say, similar to how I mentioned before, we can calculate a value that when sent alongside the message allows the receiver to verify the message is intact, right? Now, how this happens in practice is there's a shared secret key that is exchanged between both parties. So they're both able to calculate any MACs that come through. And the MAC function itself is usually, there's no guarantee of preserving confidentiality. So it could be something as simple as taking the plaintext message and this shared secret key, concatenating them together, and then taking the hash of that. So then that is sent onto the other side. And then the receiver is able to then, okay, I have the shared secret key. I have the plaintext message because I've decrypted it. Now I'm going to verify that this matches the MAC that I was given. Are there any questions that you guys have in particular about MACs? Now's the time to ask.
I could ask one, I think you might have already done it, but like, why would you need a Mac?
They're
Why would you use it?
a very good laptop. No. Okay. We'll just jump back to the Shrek movie again for a sec. If I have Alice and Bob and then Eve in the middle, Alice encrypts with Bob's key, the public key, the Shrek movie, and then, what she thinks is Bob's public key, but it's actually Eve's, then sends it across without a MAC. Eve is able to decrypt it because Eve has Eve's private key for Eve's public key, and maybe change it to be Shrek2. And then re-encrypt it using Bob's public key and forward it onto Bob. Bob is none the wiser because there is no MAC between Alice and Bob. Now, obviously, MACs are not a complete killer for these kind of attacks, but suppose that Alice and Bob had this shared key that Eve did not have, then when Eve, man in the middles, or monster in the middles, Alice and Bob, they're not able to switch the movie out from Shrek to Shrek 2 because the original Mac will still be for Shrek. I promise I don't have an obsession with Shrek.
I think there's another example that comes to mind that I think is relevant for if you use an encryption channel between two parties, if you use an encryption channel between two parties to talk, and it's public-private key, like the encrypted result is not necessarily different if you send the same message, right? Because the encryption, unless you introduce randomness, is a one-way thing, right? Like if I encrypt the message hello with a particular key, you get the exact same result as if you were to use the same key and encrypt hello again. Like it sounds a bit redundant. But the point of that is that like if you have a communication channel with someone that's encrypted and then someone's watching the whole thing and they save everything, they don't even need to know what's inside it to know that they could send it again with a replay attack or whatever. And it would still be decrypted as valid, right? So I think one of the points of Max for say SSH, for example, is that yes, you've got your public-private key on each side that gets you an encrypted channel, but you also would negotiate a one-off symmetric key to use for a Mac, such that every message you'll send, you know, is being sent in that current session, and it would be infeasible for it to be like, even though you're talking to this person, you're going through the internet, right? Like, you don't know if someone's fiddling with stuff in the middle or not. And so if someone was capturing all the traffic coming from the other side, storing it somewhere else and sending old stuff instead, like you wouldn't know, you wouldn't be any the wiser unless in this example of using a Mac based off a shared key each time, the Mac wouldn't match, right? Because it's a unique key for that session. And so they couldn't have pre-recorded a previous session or something like that. It makes more sense if you think about, like, I think when I did this subject, Vanessa Teague was involved in running it, who was at UniMel for a while, and her specialty is internet voting and or why it's a bad idea. And a classic one is like if someone's issuing a vote or post request or whatever that has consequence, right? Like you may have heard about idempotency from HTTP and stuff like that. Like casting a vote is an important decision and you don't want a vote to be able to be accidentally cast twice, right? So that's a classic replay attack example. Like if you've got an electronic voting system and someone can resend old traffic to make votes count again, like that's really bad, right? So yeah, hopefully that helps motivate Max a bit more. They're a tricky one, right? Yep, question.
What about that? So within a session, like you still replay stuff, but it's just you have to negotiate a new match and then make it on.
Yeah, it's not true of all of them. Like the more complicated TLS, what's it? Okay, here you go. Question for the class. You can answer this. We just told it. What is electronic code book a thing of? Like, what's its categorical term? It's not a block cipher, right? Because the block cipher is the thing that works on a particular block. What's the categorical term for it? Like there's ECB and then what's the other one?
CBC.
CBC. Are they block ciphers?
The ECB still chops it up into blocks. That's why it's
No, but
parallelizable.
It's like the chaining method or whatever. Are they called?
That's the other one. Yes. They're both part of AES.
Anyway, the idea is that like AES is a block cipher in that it only operates on a fixed amount. So if you want to use variable size data, you have to string them together in some way. We saw electronic code book as a bad way of doing that because there's no diffusion, right? And you get the patterns in the image. So feeding stuff through is good. There are other ones like they use weird Euler counters. It's weird whack maths. You can look it up. I don't know how it works. I can't remember. I haven't dug into it. But like it does this crazy maths counter stuff alongside it such that the information going into it is on the basis of some magic mathematical sequence that has to be correct on both sides or something like that. And if you dig into real TLS ciphers, you'll see that's what are used nowadays. So does that answer your question?
Not sure.
What was your question?
The question was that I think you were saying motivation for the Mac was preventing replay.
Replay within the same session. Yeah.
And that's what happened on.
Yeah, so within the same session, yes, I guess, unless you have some sort of pseudo-random sequential generation. This is the whole thing, right? Like, there are always examples you can give of like, if you're talking about network examples or whatever, like, and you're reading out of a socket, like, if someone says hello, 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 and they've sent it 4 times, like, how do you know they actually sent it 4 times? Like, I'm trying to come up with a good example of it, as opposed to maybe at lower levels, like things got copy pasted and retransmitted. In a similar example, why was I bringing that up? Yeah, for encryption, it's the same thing, right? Like, actually, it's more important, I think, for encryption because it's like, if someone is able to replay chunks of your session or like take a message that you've received and just send it to you 4 times in a row, and then you interpret that as decrypting to hello 4 times, that's not what the person sent you, right? So they were able to tamper with your session, even though they didn't necessarily fully decrypt or understand what's inside it. So yeah, that's why that propagating information is useful. To the more specifics of it, that's why you would use something like a counter or something like that, some sort of information that propagates as the session continues, so that you can't just resend previous encrypted blocks and have them show up again as stuff that would let other people fiddle with your session or whatever.
And then counter back.
Yes, I don't know, very primitive example. Imagine you take the private key and instead of using it each time, you add 1 to it each time or something like that. That's something that means that it's replay safe to some degree.
We should definitely keep going.
Yes, but I hope that helps explain why Macs are useful more than anything.
If you're more interested in mitigating replay attacks and things like that, I highly recommend information security and privacy, which will be running next semester too. Cool. Any other questions on Macs? No? Awesome. Great. Okay. So as I mentioned before, Macs themselves do not preserve confidentiality. They make no guarantees of it. I could have a really poor Mac that simply outputs the plain text as its output, right? It takes in plain text or a message and a secret key as an input, and it spits out something that is meant to verify the integrity of the input, nothing more. So we can solve this with this paradigm of encrypting, then macking. So that's just saying, instead of feeding the Mac the plain text, we're going to encrypt it first, and then we are going to produce a Mac. The other upshot to this is, on the receiving end, we don't have to decrypt to verify the integrity of the data. It also means that we're not going to be decrypting anything malicious if it was tampered with. Any questions here? Nope, sweet. There we go. Cool. Okay. Any other concerns about Macs, or are we all happier with them now? Cool. All right, great.
Silence is affirmation.
Yes.
Do you want to cover digital signatures as well? Or are you pretty happy with them? I'm seeing nods. I'm going to take that as pretty happy, unless anyone wants to raise their hand now.
Hands up, digital signatures.
Cool.
No takers? All right, sweet. The slides are here.
The easy takeaway for signatures is like, you should know the function structure, so to speak, for encrypting and decrypting with a symmetric key, encrypting and decrypting with an asymmetric key, and how to produce a signature and verify a signature with an asymmetric key. The arguments, so to speak, of key, signature, and the way you get the output and such is different in each case, right? So yeah, that's what you want to be able to quickly explain. Like, what is the loose pseudocode function for verifying a signature?
They're on the slides
There you go.
for anyone who's unsure.
Yeah.
For each of these, the primitives should be up top. So Mac, we had tag, Mac with the message and the shared key up top. And digital signatures also have that for people who want to revise their exam style questions. They're very particular about using these primitives, so be careful with them. When you're talking about digital signatures as well, do not refer to public and private key. Now they are verification and signing key, respectively.
Oh, really?
Private key is signing key because it provides non-repudiation. That is, the entity that signed it is the same entity that produced the message. If I sign something, I cannot deny having created the signature because it came from my private key. That doesn't guarantee authentication because there's no way that you can guarantee up to this point that the public key or the verification key used to verify the digital signature is actually mine. You found it off the internet somewhere. Who's to say it isn't Stuart's or anyone else's?
It's a matter of like, the signature proves ownership of a key, but is that the right key is the question. And that's kind of the whole reason certificates exist, because it's to prove, it's to give name or person attestation for a particular key. Like, this is not just key 1, 2, 3. I'm saying it's Britain's 1, 2, 3 key, like, and I've staked my reputation on that being his key and no one else having that key. So yeah, it's that thing of like, just because you can establish an encrypted connection with public-private key pairs or whatever, doesn't necessarily mean you have established the right one, because it could be any key pair as far as you're aware, unless you validate it somehow. No, so yeah.
Any questions, sir? No, awesome, okay. As I mentioned, because we are creating a digital signature, it's very similar to a Mac. So it provides integrity. And as I mentioned before, also there is non-repudiation, but no authentication. How are we feeling about certificates? Do we want to go through them? At all? Hands up or yes?
Do you want to go through them or are you happy? Okay, thumbs up.
Everyone's cool? Amazing. Long and short of it is, this is how you get to authentication and trusting public keys. So these are here, and I'll come up with a PKI question to go on the question document after this. Great. Yep, so here we have root certificates. They get shipped with the operating system in the browser, and that's where your chain of trust terminates. And so does cryptography. So now we have questions or a 5-minute break.
Let's actually take a break because we are halfway at this point, and we should take a break.
Can you clock networking in like 25 minutes?
Try my best. My plan for networking is to give a, like, from the physical up explanation of it. I think that's a better way to teach it, because every layer of the TCP/IP stack is motivated by the limitations of the layer below it. We'll see that more. Yeah, I think I might even do another Excalibur draw. We'll see. But yeah, so just take a break. Think about something different. Like, I don't know, puppies or something different. I remember a lecturer said to me once, there's been a lot of research. We had these 2-hour lecture slots and they did 45 minutes, then a break, and then they'd do another 45 minutes or whatever. And they said research has shown that, like, you don't actually retain information before some certain point if you're going all the time. So breaks are good. Breaks are important. Let's take a break.
I'll throw a 5-minute timer. If you guys have any questions for OS or crypto as well, I'm also happy to discuss.
Yeah. It's this one, not about the subject though.
I feel like it's very easy to stay.
I don't know where the links are, I guess. I want to look for. What the heck?
What are you trying to look for?
Why is like is it because caps lock is on? Like, why does Command T? Alrighty, folks, I've been told it's 5 minutes.
Me, I heard. You know, I went to the.
Okay. So if I can have your attention again, can you all hear me? Hopefully, good. What I'm going to try to cover now is a walkthrough that I hope will cover the bottom 2 points here and act as a motivation through all of these things. So yeah, there's some, it's a little unstructured, but we have here, these are the slides that are left over of like why there's this layered model of the internet. You should all kind of know at this point, it's motivated by services provided by each layer, right? So at any particular layer, there are limitations to what you can do, but there are reliabilities to what is available. And you can use those reliabilities as the basis for building something more complicated by using extra data and protocols atop the lower layers. How do I describe this? Like, at the lowest level of, I'll just quickly briefly mention as well, you should hopefully have an understanding of how the layers correspond to encapsulation of packets. The Wireshark practicals make this really clear because like they would show you the exact bytes from say an Ethernet packet, and there's got this little UI in it, and it'll show you, well, what parts are like the elements for Ethernet of like length, MAC address, things like that. And then that includes a chunk of data that is a TCP thing. And so it's this wrapping, so to speak, of stuff. Where I start with this is like, I want to start at the bottom layer, which is Ethernet. So, and kind of motivate why we're talking about all this anyway. So, Ethernet is all about like a directly connected network. So there are technicality exemptions to this, but in general, if you're on an Ethernet network, or a network, you're supposed to have basically a direct line connection to any other computer on that network that you're trying to talk to. The common example like this, I give in rooms where there's desktops with LAN cables in them, is that each one of those computers has the ability to directly talk to every other computer in that room because they're all wired into one box, basically. And I'll just quickly at this point talk about like where this starts, because this does motivate to some degree of the difference between hubs and switches. Has anyone heard about these two things? I became aware of this from my high school years where like we always had a hub, like every room, it was before Wi-Fi was as reliable, and each room would have power board in this wooden carry thing that had a network hub in the top of it. And the hub was what everyone plugged their LAN cables into to play Halo with each other in the middle of class. But hubs are quite inefficient because the way that they work is that when you send any Ethernet packet, for this example, the hub broadcasts that packet out every other cable. And so that works because it ends up getting to the place that it needs to go. It's very simple, but it's quite inefficient, right? Because in this case, we've got these 4 computers. A wants to talk to C, and it sends a message, and it gets sent to all of them. So in the Ethernet protocol, this is where, like, if you see a frame that comes in that's not for your MAC address, you drop it. Really old versions of Ethernet used to be like a really one long cable that you tapped into points of. So it's like one shared communication medium. That's the way to think about it, right? Like it's one physically wired network. Switches make things a bit better by keeping track of the MAC addresses plugged into each port. And on the basis of that, we'll deliver a packet only to the right destination. So that improves it a bit because like now two people, you can have, say, two communication pairs going on that can utilize more bandwidth because the data is not going everywhere now all the time. If you're sending like a 200 megabyte file from one computer to another, that's going to be a whole lot of Ethernet frames. It'd be really annoying if you were using the network with a hub and other people are transferring files and it slow down your network connection. So the question is like, why do we even have IP addresses when we've already got this thing? And the answer is because of two main things. First, even this packet switching doesn't really scale very well. Because like you need to keep track, or the equipment in the middle needs to keep track of every single unique address that's going on in its context. Like it works if you've got like 30 or so devices, maybe even 100 or 200, but like beyond that, like if you scale it up to the number of devices in the internet, your one box would need to be able to know about every physical address everywhere in the world, and that's just crazy impractical. So that's one reason why we have all of this. And then also, like, they act as domains for broadcasting as well. Like, broadcast packets are still possible on Ethernet. You can send a packet that will go to everyone on the Ethernet. This is how the address resolution protocol works for IP. If you need to find out who on your network has a particular IP address, you use the address resolution protocol to send a broadcast frame on your local network saying, hey, I want to know who has IP address 123. Please tell me. And that frame has a from address that is your MAC address. So that gets delivered to everyone. And similar to what we were saying before. So even with a switch, broadcast packets still go to everyone on the switch. And you know, you get data frames in all the time. If you see one come in that's a broadcast, you'll get it. And if you get it and it's your IP address, so it's not your IP address, you go, I don't even care about this. Like, I don't know anything about this. It could be false, I don't know. But if you receive it and you do have that IP address, because that's the IP you're using on your network, you have received a message saying, like, you know the sender MAC because it's the sender and the destination is the broadcast address. So you take that sender and reply back to it saying, hey, yeah, it's me. I have this address. So that's how Ethernet and IP kind of bridge to the point of being able to get IP addresses used for communication on the same network. And even on one network, this is still useful, which is because the other thing I mentioned here is that MAC addresses don't change, but IP addresses do all the time. Every time you connect to a Wi-Fi network, you may well get a different IP address, for example. DHCP is another magic protocol that auto assigns IP addresses when you join a network for the first time. But even so, like if you have something running at an IP address and the server breaks and you need to replace it, like it'd be really annoying if you had to tell everyone that it was on a different address now, right? So that's part of the point of IP addresses is that they're a lot squishier. You can change them, and they can be different in different networks and stuff like that. So this is a loose explanation, but hopefully that explains it. There's this fun thing that a friend linked me, and we saw this, the wiki for Doom, the original first-person shooter, has this info about broadcast packet meltdown. That the first version of Doom used broadcast packets to say where you were in the map, and like that kept pissing off like network users in schools or whatever, because like someone was playing Doom and then they're like trash the network performance for everyone else because everyone's getting all of these like broadcast frames all the time. So you can imagine if that's possible and you open that up to the internet, like it'd be chaos, right? It wouldn't be feasible to communicate. So hopefully I've helped motivate some of that. And yeah, even with switching, there are problems with loops. I didn't even know about this, but yeah, if you get switches and you chain them into a loop, they don't know that they're in a loop and they can send packets around and around and around. And so, because the switching is only happening at the Ethernet layer, there's no IP packet forwarding happening. And this is the difference between switching and forwarding. So switching is when you're on one Ethernet network. It's like just moving stuff to the right cable on the current network to get it to the right directly connected person. But forwarding is when you take two different networks and say, okay, now I want to provide the ability for people on this network to talk to people on this network. And that's where routers come in, essentially. So hopefully this helps motivate some of this a bit more. At this point, I think I don't trust the whiteboard being visible to everyone. So can I just share this entire screen? Yeah, okay, bingo. And do my old Excalibur trick. What? Why is this happening? This is a whiteboard. It's just on the computer. So the example I always give, this is fun. Not in Bouverie Street basement anymore. We're in Arts West. I usually give the example of talking between Bouverie Street and Arts West, but we'll have to do it the other way around this time. With what we were talking about before, on a particular Ethernet network, like, all right, let's imagine we are back in Bouverie Street, purely because that's where there's physical computers with cables plugged into them. I feel like the analogy works better there than Wi-Fi, where things are a bit more nebulous. So these computers are all in one room, and they talk to each other via a hub or switch that facilitates Ethernet level communication between all of them. So they're all directly connected to each other. Like they are within one wired network, so to speak. There's a direct connection between any of them. If they know the MAC address of the thing that they want to talk to, they can just drop the frame on the network and they know it'll get there. Because there's no huge magic amount of hopping going on. The guarantees of Ethernet as a layer for communication provide this. And like we said, there are limitations to this that like you wouldn't use Ethernet for having one giant internet because it's infeasible with the MAC addresses and so on and so forth. So again, this is where routers come in, and they often have, can I do the double? Oh, yes. I can do the proper thingy. All right, that's not quite connected. Bingo. I can do. It's just, this is the thingy. They always have this on routers, right? Like the two arrows going back and forth. So routers are supposed to provide this ability to talk, to allow communication between different directly connected networks. So again, we have this example of like, say, Bouverie B127, we'll call it. And ultimately, like this router is going to also be attached to that network. And there's going to be a MAC address associated with the port on that router because it participates in this network within that one connection that it's got to it. So we'll say it's MAC ABCD. But in addition, for argument's sake, we'll say that, what's another room in Bouverie? 114? Yeah. There are more computers in this other room, and we're going to say that they're not kept on the same direct network. Maybe this is a cooler classroom and there's one extra set of computers. So, yeah, when working with routers, typically the way to think about it is that there's a port on the router for every particular network that you want to facilitate packet forwarding between. So this is why when you see routing table examples, it's always talking about what interface is associated with a given network. Because what routers do is provide the ability to accept data destined for other networks. And we'll walk through this now in the sense of like, if we say that this is 172.16.1.0 slash, what is it when it's this? Is it slash 16? Yeah, I think we'll call that the IP address, so the network we've set up for this building, and it'll be 2 for this one. So network addresses is a whole other thing. We're using this /16 is for a subnet of 16 bits. IPv4 addresses are 32 bits. they are 4 octets. There's 4 numbers there. The numbers go from 0 to 255, right? You would have seen. 0 to 255 is 256. 256 is 2 to the power of 8. There's 8 bits. 4 chunks of 8 bits are padded into one 32-bit thing. That's your IPv6 address. IPv4, yes, good catch. And the subnet mask is a number of bits from the left that are kept the same for all devices on that one network. So in this case, it's actually, this is incorrect. Someone didn't catch me. It's /16, so it only goes to the middle. So I should have used 192 is, oh, that's more common. So these two have to be different. The reason for this is that 16 is 8 times 2. It's 2 octets. It's a clean example of where like the bits coming from the left line up exactly as 16, which means that the first 2 octets are always the same for everyone in this one network. And actually at this point, this is where we need to draw one of these, this big old diagram. I do have .17 trust, thank you. Yeah, if I make mistakes, please let me know. You all know when I make mistakes, right? So yeah, so that's 17, this is 16, yeah, okay. Catch. So what I want to highlight on specifically here is like, how do you communicate to the different network? You've got IP frames that you can put in Ethernet. With Ethernet, you have the ability to deliver messages to anyone on your directly connected network, but you can't get to the other network. But you know, based off, we'll say, hearsay or configuration, that there's a router on your network it's often called the gateway, right? It acts as a message deliverer for other networks. And you've got the ability to communicate it with Ethernet. So if this is like .1, 2, I'm gonna have to do all these, do 2 of them. So these are just like 172.17.1.2, so on and so forth. If someone in 127 wants to communicate to a server, a cool Minecraft server someone's running in B114, they need to know the IP address of it, we'll say, for simplicity's sake. But they need to send an IP packet from 172.16.0.5, we'll say. It's just being the numbers are different, it's easy to explain. And they want to send it to 172.16.17.0.2, we'll say. So whilst it can't directly talk to that computer, it can talk to the router. So the whole key to how packet forwarding works is that you take the IP packet that you want to go somewhere else and put it in an Ethernet frame addressed to the router. So where is it? I'm going to be able to make this. And when the router receives this packet, we said in the tutorials, routers do have IP addresses. Often they serve their own web interface for configuration. You might need to contact the router directly to ask it stuff anyway. But the whole thing is that when you're using the forwarding services of the router, the way you do that is by delivering it an IP packet that has a different destination address to that of the router's actual IP address. So if this is .255 or 254, we'll say. If you know where the router's IP address is, you can use the address resolution protocol to find its MAC address. You've been told that that's the gateway for this network. You use that to deliver it an Ethernet frame containing an IP packet that is bound for the other network. And the router will do forwarding to copy the packet over to the other network. But at this point, things change because it can't use a from MAC address on this network when it's delivering it over here, because that MAC address is not part of this network. Like, it's not directly connected. It's separated by the boundary of forwarding that the router is doing. So it copies the IP packet into a new Ethernet frame. And instead will, it participates in the network and uses address resolution protocol itself, right? So it can ask on the network who holds address 17.0.2. It can use that to work out that it's, this is going to be, this needs to be different here. We'll see, call this BBCD. So in this case, it's come from BBCD, which is a different port on the router connected into this network. And we'll say it goes to DD, which happens to be what NOD is. So hopefully stepping through it this way explains that link between the two of them. The whole reason we have IP and routers for forwarding is because Ethernet networks don't scale beyond like a building or two, generally speaking. Like, you run into massive problems, broadcast domains, packet switching stuff. Like, it becomes way too complicated to keep track of all of the MAC addresses. So you break things down into these networks in the Ethernet level and join them together with routers that have the ability to forward packets between them. Question?
It came up a few times that, let's say, routers have multiple IP addresses.
Yes.
I'm not even sure why they have one, if they're just, there's an IP over here, and let's get it over there. I mean, just go, oh, I know which MAC address.
How do you know the MAC address of the router when you join the network? What do you have to do to get an ARP request? You send a broadcast packet, right? What's inside the broadcast packet?
Everyone's wanting MAC address.
That would be bad because, well, it's like if you're on a big network, like, everyone's going to tell you all at once. And ARP doesn't really work like that, in the sense that the request is, you see this in Wireshark specifically, if you see ARP packets, it says, who has this IP address? You're trying to find out the MAC address of someone who holds a particular IP address. So the only way to get the router's MAC address is to use the address resolution protocol to ask on the network, hey, I was told IP address is this router. I need to find out who's holding that IP address on this network. So the ARP doesn't have anything specific to it being a router. But
you find it.
Great question. So with DHCP, it delivers that information to you when you join the network. In ye olden days, you had to configure that properly yourself. So if you didn't configure the gateway properly, certainly like in Windows IP settings, it was always the gateway section. In more complicated cases, gateway is a generalization of default routes. It's like one default route, basically. And so the gateway is supposed to be the IP address that you can talk to communicate using IP beyond your direct subnet and to other networks, so to speak. Does that make sense?
I think so.
So that's why routers need IP addresses, right? Because what if you replace the router? Like, you don't, okay, say you've got a classroom, say you've got Bouverie Street. How many computers are there in Bouverie Street? Let's say 200, right? Router breaks, you need to install a new router. Are you going to go through and change the network configuration on all 200 computers in Bouverie Street? I mean, maybe you really like network configuring. I don't know, but like, that's part of it, right? It gets back to what I was saying before. It's the squishiness of IP addresses, right? Like, anyone can take them on. So you can swap out hardware without having to change the logical configuration of how things are run. So yeah, that's mostly what I wanted to get through, I think. Beyond this just starts scaling. Hopefully you understand that things just start scaling up beyond this. So we'll say, within UniMelb's domain, I'm just going to get rid of the numbers and stuff because it's just illustrative. Unimelb has a bunch of different buildings, right? Say we are over in Arts West. Which room is this? It was 361. Thank you. And hey, let's do something different. Like, maybe this is Wi-Fi router. Wi-Fi routers provide Ethernet services using wireless communications. If everyone is connected to the same Wi-Fi router, you have the ability to deliver Ethernet frames to anyone else connected to that particular router. And so from here, a router would also be plugged into a physical network somewhere. Like you look at that thing, there'll be a cable in it going back into a router somewhere else in the building. Maybe there's another room. And then in addition to this, like there might be a fiber link between this building and Bouverie Street. So that provides the ability for people at Bouverie Street to play on Minecraft servers in Arts West, so to speak. But beyond this, then things start bridging out to the broader internet, right? So these are probably also gonna have direct links to some internet point in Unimelb, so Unimelb, Carlton, so on and so on. Then you start bridging into the internet. At some point, you move from private networks to the internet. There's, give me a second to dig this up. This was another thing that I showed people who happen to be studying the subject to kind of motivate some of the did I get that right?
Make sure it's time for TCP and such.
Yeah. 10148. That's what I'm just about to get to. AS 10148. Did I get that right? Oh, I missed the S. This is Unimelb's public set of IPs. It's got quite a lot of them. On the public internet, it snagged this very nice looking 128.250.0.0. There's quite a lot here, but like University of Melbourne has a number of different sites, right? And if it owns IP addresses and wants all of its different sites to be accessible via the internet, like it needs to split up the IP addresses that it has to be able to allocate them to those different buildings or like different physical locations. From there, the routers will be able to communicate to each other and receive and transmit traffic. At this point in the story mode explanation of all of this, we kind of have to move to network address translation, which I just realized was something I didn't even put on the initial slide list, but I will move back to the what's it now, because where are we at?
Should be at the very end.
Okay, well, it's
Might be better to try
2 minutes. Yeah, okay. Let's, first of all, hopefully that helps. That I like to think motivates the bottom two layers. And I think it's better to go from the bottom up to kind of explain why this happens. Like, why do we need TCP? Well, routers are kind of reliable, but if links get really busy, they have to drop packets. The classic example is if like someone's watching Netflix 10 times or whatever, and they're hogging a particular internet link. More data is coming in to one end of a router than it is capable of sending down, say, a 100 megabit cable. It's got two options, right? It can try and buffer some of the information and hang on to it to deliver it when it's got the capability to, or it has to just drop it. And in general, that's what it does. It'll just drop the traffic. Because of that, when links get busy, the internet or the network is not reliable. So you need something like TCP to be able to cause retransmission to happen to engage and give that reliable delivery. What I was going to say was, if we quickly look back at the start, which of the network topics, this is the problem, right? I think it was all of them, right, that we wanted to cover. I feel like hopefully I've motivated these bottom two and touched them somewhat and explained them. The sliding window and congestion control, Are those ones that people want covered? Which of these confuses people the most, or would they like to see covered in the rest of this?
Hands up for sliding window. Okay, now hands up for congestion control.
Couple for congestion control. What about application level protocols? Is anyone confused about any of those?
Do we understand HTTP? Hands up, yes.
Who remembers that?
Okay,
All right. Well, let's look at sliding window, I guess.
Yes. see if you can do what? 8 minutes sliding window, 8 minutes congestion control.
Yes. So what is the reason why we have, does anyone know off the top of their heads the answer? So this is a reasonable exam question, I guess. Why does TCP have the sliding window protocol? Like why is it useful? Kind of. Yes, so it's a little tricky. It's not the sliding window per se that provides the reliability. The acknowledgement process guarantees the order, right? So yes, that is part of it. But like, it's a window, right? Like it gets bigger and smaller. Like, why do we care how big that is at all when we've got the numbers and acknowledgements anyway? Like, so the window size is an extra parameter, right? Like you can send an ACK packets, and that alone gets you the ability to do reliable delivery, right? Because you can just ask, if you send an ACK, what does sending an ACK packet mean? It's got a number in it, right? There's an ACK number. What does that, the fact that you've sent that packet mean? So it's ACK 120. Yeah, I've received everything up to this point. So if you deliver that multiple times, that's the way TCP is capable of communicating, so to speak, or ensuring communication occurs to deliver stuff. But like, so that alone is enough to do it. With the sliding window particularly, it's a window that can get bigger and smaller. Why is that important?
A quick interjection. Your acknowledgement number is going to be the number of the byte that you're expecting next, as opposed to here's what you've received.
Yeah.
That's not.
I always get these specifics wrong. I'm really sorry, but like conceptually, the acknowledgement is communicating that information, right? The reason the window exists is to not send too much data at once to the computer on the other side, right? So the computers can get busy. Lots of processes run on a computer. It might not be possible, depending on how busy the computer is, to always read all of the data out of the network card that is ready to be read if the computer's in the middle of doing something else, right? So network packets come in totally randomly, right? They can come in anytime. And especially if delays start getting introduced into the network, you might end up getting just a whole ton of them all in one go or whatever. And that might arrive at a really bad time, like say you're in the middle of writing 4 gigabytes to disk or something like that. And you're really busy, the computer's really busy and occupied with that. So the whole reason the sliding window specifically exists is to bound the amount of in-flight data being handled at any one point, so that no more than is necessary is sent. And that's where it comes under that flow control, so to speak, right? So it's to ensure that no more retransmission happens than is necessary. Like if a buffer's full and it drops a bunch of stuff because there's too much for it to hold, then retransmission is going to need to occur, right? That's a waste of network space if you can control that. So the sliding window, so to speak, guarantees that no more is delivered than is capable of being received to reduce the amount of retransmission. Question?
Yes, I've sort of a few questions, but first of all, you can still have TCP can still be reliable in order without the sliding.
Yes, because of the sequence and acknowledgement numbers. So purely with that, like, the frames can be sent and delivered in any order, but the ACKs go both ways, right? And the ACKs are received and they act as confirmation that you got stuff in order, right? It's not just, oh, I received this packet. It's, I've got everything in order up to this point. So purely on the basis of that, it provides the reliability and the in-order guarantees. But the sliding window specifically just bounds the amount of data that is ever sent back and forth in one go to stop. Like if you try to deliver 2 gigabytes to someone else's computer over TCP and they've only got 50 kilobytes of buffer, we'll say in the network card, like there is no point trying to send the 2 gigabytes of packets in one go. Like what's it? 2 gigabytes, subtract 50 kilobytes, that's what, oh, hair splitting 1,999 megabytes and blah, 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 blah. That much data gets wasted, right? So if it wasn't read in time. So that's the whole motivating reason for the sliding window in particular. Does that make sense to people? Hopefully it does. So if we've got the sliding window, why do we need the congestion window? Does congestion necessarily have anything to do with buffering on either side of a network? No. Where does congestion occur? Yes, in the middle of the network. So this is why it's a bit different. It's a separate mechanism to also control the amount of chunks of data going back and forth, but on the basis of what is observed. My understanding, if I remember correctly, is that like it's based on watching what packets get dropped and the sequence of packets getting dropped and stuff like that. Like if you keep receiving acknowledgements that aren't up to date, then that's a hint of sorts that packets aren't always getting through. So for example, if a pipe in the middle is really congested and it can't handle 2 megabyte payloads, we'll say, because all this other stuff is coming through. And you keep trying to send 2 megabyte payloads with TCP, and they keep getting dropped. What are you going to see from the other side of the connection? Like they're getting dropped, so they're not making it there. What will you see from the other side? You won't see ACKs of the 2 megabytes you sent, but what will you see? You see ACKs for the earlier number, right? Because in TCP, if you haven't received data in a certain time, you send an ACK with an expectation of like receiving more of that data, right? Like the ACKs have to be retransmitted if they have to be retransmitted for you to be able to communicate packet loss, if that makes sense. So on that basis, if you keep sending 2 megabytes and keep getting ACKs back for the previous number, then that's kind of an indication that it's not getting through, right? And so you can use that as a signal to say, reduce the amount that you're sending. And as to the specifics of this, there's the slow start, and then if it detects packet loss occurs, it tries to drop, and there's the fast recovery. Like they did a lot of research on this and a lot of testing, is my understanding, to work a lot of this out. The point of the slow start is to try and expand to fill as much of the bandwidth as possible before such time that you start to notice packet loss. Because if you can deliver more data in single goes, that's more efficient, right? Overhead is involved with every single TCP packet. You've got to put in the sequence number, blah, 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 blah. You've got to put all the wrapping and all that kind of stuff. So the more data you can fit into single chunks of TCP in one go, the better. but not if you try to fit so much that it can't get through a particular link or something like that. So, yeah. In terms of questions you'd get asked, I'm not sure whether it's feasible that you'd be asked to step through. There wasn't a congestion window flow question this year, was there, in the workshops? There was definitely a
They handled it in the crack, but it wasn't mentioned at all in any tutorials.
yeah.
There was an entire crack around congestion.
There was a tutorial on the sliding window for sure. The question on that is really good. And we've come up with another one, haven't we?
We're coming up with another one. The sliding window question should be sitting in week and tutorial.
Yeah. If you haven't stepped through that, step through it, because like you could absolutely easily be asked to do something like that in an exam. It's motivating why TCP exists, right? And if you go through it, you see it happen, right? Oh, this got dropped, the ACKs played out, and it caused retransmission to occur. So yeah, that's my quick attempt at getting through congestion window and sliding window. Hopefully that helps. It's this hair splitting, right? Of just like which bits technically provide which guarantees. It's a bit hard to explain given TCP is so complicated. It's been extended multiple times. The congestion window stuff, I think, was added later. Selective acknowledgement was added later as an extension, all sorts of things like that.
Whatnot.
Yeah. We've reached the end. We've run out of time for network address translation, which is what I was actually hoping to talk through. Are there any burning topics that we haven't covered that anyone would like me to talk about?
Or is anyone confused on anything that's been talked about so far
It's perhaps a better question.
that would like to have something rehashed in a different way?
If not, I might at least briefly show these network address translation examples that I put together previously. Again, I try to connect everything to the real world and real world examples where I can. I had a great real world example of network address translation. I wanted to run a Minecraft server. So I use it as a bit of a meme example, but genuinely in lockdown, we had nothing better to do. So I ran a Minecraft server on my home network. Let's come back to this because basically I discovered most internet these days, so you keep hearing the story, they ran out of IPv4 addresses, right? Or like, we're going to run out of IPv4 addresses, and there's just more and more devices on the internet and stuff like that. Turns out, yeah, we really did run out of IPv4 addresses to the point now that ISPs do network address translation to their customers. So this is called carrier grade NAT. There's a Wikipedia page about it if you're interested. What they do is do network address translation such that multiple ISP customers share one public IP address. And it might seem a bit crazy, but network address translation works. And also, 90% of people using the internet don't need to receive connections. And it's kind of, it might sound a bit crazy, but if you think about it, like if anyone's using a laptop, like what do? You rarely start a server on a laptop or anything like that, right? You open a web browser and you make an outbound connection. So because of that, that can be exploited to this because network address translation combines the port number from TCP and IP address pairs as a space of sorts for multiplexing. And it keeps track of, we have a good example here, port pairs on one network and external ports used on a particular public internet address. There's a lot of ports, right? So you can use ports as a multiplexing mechanism of sorts to let one IP address be used by a lot of different people if you split their usage across the ports and then just translate the port numbers back to things when the packet arrives at the router, it's addressed to the router's one public internet IP, but it's TCP or whatever on a particular port. That combination is used to map back to the right local destination IP address. and it rewrites the port number as well as the IP address when it moves across those boundaries. And it works, basically. It lets you share one IPv4 port between multiple things. So I have this example here. The downside of this is that if you want to accept connections on a particular port, the connection request comes into the one public v4 address on the one port. And then there's however many network devices behind that. Which one should it go to? Well, you can't say unless it's explicitly configured. And this is where, like, in home routers, there'll be like, you can configure network address translation rules or whatever. If you want to hold a Minecraft server, I think I found it, yeah, it's port 25565. So you have to configure your router to forward connect requests from that port through to your local network address on that port. You can actually change it to be a different port if you really want to, but that's kind of doing that multiplexing, right? It's like saying, well, if these connect requests come through, the router itself doesn't run a Minecraft server. Like, the main thing it does is packet forwarding. But what it can do with network address translation is accept it, if it sees connect requests, it can rewrite the packet before delivering it on the local network to say that the connection request has it just changes the destination IP address to be not your IPv4 internet address, but the local network one. So are we out of time? Just about out of time. Hopefully that makes sense as a quick explanation of network address translation. It's kind of like a next level of routing in some sense, right? Because we were talking about before, routing is for forwarding IP packets purely between networks. Routing alone has nothing to do with TCP or UDP explicitly. Like, that information sometimes can be taken into account. This is where you hear things like they talk about the difference between a layer 2 switch and a layer 3 switch. But in principle, so to speak, the basics of routing only need to use the Ethernet level and the IP level. What's inside the IP packet, let it be UDP or TCP or whatever else, doesn't matter when it comes to the basics of routing. But with network address translation, it extends it a bit further by taking the TCP level information into account, namely the port number, because the port number, there are no ports at IP level. Like, IP lets you deliver a chunk of data to an IP address. It doesn't say anything about there being a port involved. The port comes into existence at the point of TCP and UDP. If you look into the frames, like, I can Google it, right? Like, if you search TCP header, source port, destination port. The ports only exist within the layer of TCP. Yeah, transport layer. Are there any other general questions? I hope this was useful. Like I said, I'm of the opinion that the subject gets the network segment the wrong way around and just start at Ethernet and go up to kind of motivate things that way. Maybe it's a difference of opinion because maybe application's a bit softer to start with, but I think the motivation works better when you go the other way around. Are there any other questions? Are there any topics people are still scared about even after today? People are probably still a bit nervous about TCP, sequence numbers and stuff like that. The best advice I can give for that, like, we can talk all day. We can walk through more examples, but like, you got to be able to do the numbers yourself and see how it slides. The example from the workshop is pretty straightforward. You will have the solutions at this point. Like I say, if you step through it, it motivates the whole thing. You see the packets disappear. You see why the retransmission happens.
We also have a modified version of that question, which I'll draw up solutions for tonight and invite you, and there will be that available as well. I also strongly encourage people to ask questions on Ed.
Yes.
And at this point, I'm quite happy to hang around for a little longer too.
Yeah, and me too. If you have any specific questions, feel free to ask.
And we can work through our tutorial questions or whichever, because yes, we have run over time a little bit. Generally, I'm pretty passionate about this slide. Yes, the subject is quite broad, but at no point does it get particularly deep. So, right, yes, definitely have your own notes, and if you have time, go through each of the slides, write down the title of each of them, compile a list, see what the subject is actually trying to teach you. And if any of the slide titles don't make sense or look unfamiliar, you can't reason about them, that might be a good indication to go back through the lectures and see what those slides are about. And also ask on Ed.
Can I say, my subject revision advice from, I remember literally doing that for this subject is, make a markdown document, put a bullet point for each week, put a bullet point for each lecture, and then put topics under all of them. Literally just do that to index the subject, so to speak, and go through all your head. And then look at that list and go, okay, what do I suck at? That's a really easy way for you to understand and prioritize your studies, so to speak. So yeah, or so what am I not so confident with? We'll put it that way.
Yeah, generally, the quicker you have an overview of the subject, I feel like the stronger your foundations will be. On top of that, asking questions on Ed, and in particular, I found for my year, answering other people's questions was really helpful. I know it's very daunting answering other questions because you're scared, what if I get it wrong? Something like that, right? I'm telling you now, when you make that first step, it gets a lot easier. And if you can accept that at times you are going to be wrong, then you will learn a lot quicker. In my opinion as well, teaching is a very strong way to consolidate your foundations. That may or may not have been how I got here.
It goes back to that thing I was saying about the mesh of knowledge, right? Like you may not understand everything on first pass, but every time you go through it, you recognize more, right? And there's so many interlinks in the subject that just you keep pushing through it, things do make more sense over time.
Yes. Revise the practice exam, it's out. Please also post your solutions to the questions on Ed. It'll encourage further discussion, and maybe someone might say something that you haven't quite thought about, or say it in a way that makes more sense. Yes, also if you can maybe run the lectures back, watch them from the start. I don't encourage this if you have 3 other subjects to also study for. This is like maybe if you want to do cream on the top kind of thing. And finally, I will always suggest get a good night's sleep before the exam and make sure you're hydrated. There's nothing that sucks more than doing an exam with no sleep. And I'm pretty sure that if you get a good night's sleep the night before, it's going to do you a lot more favors than cramming the night before in the hopes of polishing off 1 or 2 more marks.
Cramming was how my friend failed Cut 2 times.
So yeah, with that being said, thanks for coming and good luck to you all.
I have my MMU diagram. So this is famous me just running over time. But just quickly, I dug up some old stuff from when I did. Oh yeah, sorry, no, the slides. Sorry, that is very important. I just assume you'd already got to the end of the what's it? Yeah.
Okay.
Bingo. So here are the QR codes.
And we need to refresh it.
I don't think we
do.
All right,
Just
fine.
go with it.
So these are the updated QR codes for these slides,
Yes.
a question doc and answers that we are filling in because we had to really run through all of this very last minute.
Yep. So questions, I believe, have all been written. I'll go through them again after this. The answer is currently empty. This is partially to encourage you to take a shot at this first yourself, because you're going to learn a lot better having a go and then seeing the solutions. The other half of that is we need to deliberate a little bit more about the answers, and then we can give you a unified form of what that looks like. So you should expect that tonight or tomorrow. They will go up onto that doc.
Cool. All right. Well, hopefully everyone's having a photo, the opportunity to take a photo. Yeah. Oh yes, and feedback, very important. I need to do a feedback form for.
Yes.
Yeah, you don't like. Yeah, the uni doesn't give you anything. You have no idea. So
Yeah,
let's find out that anyway. Is that okay? Okay, this is actually the last slide now. So please give some feedback. Thank you to the CISSA volunteers for doing all the admin of getting this together.
Maybe we put the QR code on the other slide so they have all four together or something.
Did both intro.
Cool, thanks for coming. And if you have any questions, we'll be around for a little bit longer.
Well, I think we probably did the best we could given